Welcome back. So today I want to do a recap of the stream from last week, and I'm actually even still wearing the same shirt. Well, actually I did change shirts in between. I think it's a coincidence. I just looked again at the stream and I noticed this fact. So I can take this off. I don't need this. So I wanted to let's do a recap of the recap. So we're working on looking at what happens to the number of short genes when we introduce mutations. Here we're doing it by simulation, but in principle this could be used to judge the quality of genomes that we get from nanopore sequencing, where we have these indels and that break up genes. So an indel breaks up a gene, and so we end up with a shorter gene than we really have. So we've been doing this. We've been working with a handful of species, the big stars of microbiology, E. coli and Bacillus subtilis. But we wanted to start looking more broadly. We had this one idea, but I think it was time to look at it more broadly instead of optimizing just for this handful of species. So we had downloaded progenomes, and now we were going to run this on at least a sample from progenome. So let me share my screen. So we had seen that one of the stoppages one of the factors that was stopping us from doing this was that we were saving all of these intermediate files, that had the predicted proteins, when in fact all we care about is the position. So what we did is we moved the code that computed these that parsed the simulated, or the proteins from the simulated with simulated mutations, and here, and gets all of the gene positions. So and then deletes these intermediate files, right? So we parse it, and whereas before we were parsing it over and over again, now we parse it one time. We keep it as a table. We can load this table in half a second, so much faster than parsing, and we get rid of a lot of intermediate files. So we wrote this code, and then decided, okay, now that this is not going to explode in disk space, so let's run it on a fraction of progenomes. And at the time I wrote let's do 1 in 100. So we expand this progenomes 3 file. And at the time I said we were going to iterate over this big representative file, and then we use this select every nth, which uses a trick to do a sort of pseudo-random deterministic selection. So we hashed basically the genome ID we just add the word sardine in there. We hash the genome ID, and then if the hash of this is divisible by n, exactly divisible by n, then we take it, right? And we were using n equals 100. Unfortunately, when I ran it, n equals 100 would take more than a week, so I multiply that by 8 and we do n equals 800, and then I will run this a little bit longer afterwards, and we will eventually get to 100. But right, so we do this as before, expand progenomes, run check M2, and get all gene positions. So we did this ran for a few days, and there it is. So it ran over 44, 1 out of every 800 genomes, and we can now use the same code that we had before with a very slight modification. I'm just going to start running this. So this is the code that we wrote. This is basically what we've been looking at for a very long time. So here we had to do this one modification where now we're going to be loading from these input genomes, but everything else works exactly the same. We get all gene positions from this pre-computed version instead of parsing the files over and over again. So let's just do all of this. And so this is going to take a little bit longer, but the fact that the the fact that the parsing of the FASTA files is done once means that this can actually now run, and for 44 genomes, it's still very, very fast. It takes we will eventually even make this faster as we keep cleaning this up. So for example, right now we are going to be generating all of these intermediate plots, but probably we don't want to generate all of these plots like this. Right, so give it a couple of seconds there. Oops. Seconds there. Seconds there. Oop. Yep. Right, and it's generating all of these, which really shouldn't. Let's work on that tomorrow morning, or later in the evening, depending on which time zone you're at, so that when we run this, we're not generating 90 plus figures. There you are, all of the figures. These are right. But we can quickly see, see this is more or less what we expect. So blue is always wild type, and this gap there, this increase there, this is what we expect. So this is what we expect, and we keep seeing it, although it's slightly different. Oh, this one, very large gap there. Let's keep closing these, but yes, if we see that, so this is the big one, the one we were really looking forward to seeing. So it's interesting. It's a little bit of a mixed bag. So we can still see that there is, if we set the threshold low enough, say maybe minus 400 for this score, we will be excluding we will be only capturing mutated genomes, but there are some genomes there, like this red one. Maybe tomorrow we will look at what this one is, and I confess I know what it is. I just looked it up. But we'll see what I'll show it in more detail tomorrow. And these ones there, that they do seem to start off already with a lot of very short genes. So it would be nicer if we were able to somehow get a score that moves these ones up a bit, so that there's a big differentiation. So ideally we would want these. So again, these dashed lines, this is the unmutated version, and then the other lines are the lines with the mutations. So we would want as much as possible to have a score that all of the dashed lines are up there, and then the mutated versions are all down here, and we'd achieving a good separation. In some ways, if some of them, making the mistake of calling a bad genome good or a good genome bad, I don't know which mistake is worse, but yes, we see some exceptions, and we will see. And I will look at this example in more detail tomorrow. Actually, you can actually read it out. It's maybe not clear immediately which one it is. Which one it is? Which one it is that looks a little bit strange. Let's see. So let's see if that's 1, 2, 3, 4. Which can I see which one it is? So actually it's this one, it's this red one, 28903. Since I'm hinting at this, I can tell you the punchline. This is mycoplasmas, which is maybe a little bit of an outlier genome in many ways. So yeah. So let's look at this a little bit more tomorrow. Let's see if we could potentially tweak the metric we're using. Potentially, again, we're still trying to figure out if we can clean this up, seeing what's going on there, and potentially finding a better metric that could distinguish all of them. But or maybe we just have to settle for, we will set the threshold way down here at -500, and we will be able to capture these guys, at the cost of maybe missing out those. So we'll see. In the meanwhile, so as I said that we're doing every 800th. So this was also a slight modification from the code that we had in the stream. So we made this, instead of hard coding every 100th, I tweaked it so it's every n, and then I said n to 800, and so I'm just gonna add the code here, so that this would run in fast enough. And here I am changing how I'm loading the data so that it's not this pre-compute input data, but plot all processed genomes. Okay, so with that, so this is, again, everything is on GitHub, posted there. So check it out there. I'll post this on a mailing list as well. Check it out. Subscribe to keep up to date. I will be, just after posting this, and there's a link in the description below for tomorrow's stream. So that will be in about 14 hours, or depending on when exactly when you're watching this. And so see you there, and talk to you soon.